Due to the low thermal conductivity of static air, the closed air space is often used as the thermal insulation layer of the envelope structure in architectural design. The heat transfer process of the air layer is different from that of the solid material layer. Under ideal conditions, the solid material layer only has heat conduction mode, while there are three heat transfer modes in the air layer, namely heat conduction, convection, and radiation. This is equivalent to the heat transfer process between two surfaces of a finite air layer, including convection heat transfer and radiation heat transfer. Therefore, the thermal resistance of the air layer namely depends on the thickness of the air boundary layer on the two surfaces of the interlayer and the radiation heat transfer intensity between the interfaces. There is no proportional relationship between the thermal resistance and the thickness. The convective heat transfer intensity is related to the thickness, position, shape, and tightness of the interlayer. There are vertical and horizontal air layers in this figure, where finger A and B are vertical air layers, and finger C and D are horizontal air layers. As can be seen from finger A in the vertical air interlayer, when there is temperature difference between the two interfaces, the air near the hot surface rises, and the air near the cold surface sinks, forming natural convection. Finger B, due to the thin thickness of the interlayer, the rising and sinking air flows interfere with each other, making the boundary layer thinner and the velocity reduced. Finger C shows that the hot surface is above, the cold surface is below, and no convection is formed in the interlayer. Finger D shows that the hot surface is below, and the cold surface is above. The hot air rises and the cold air sinks, forming natural convection, and the natural convection heat transfer is the strongest among several interlayers. The radiative heat transfer through the interlayer is related to the emissivity of the surface material of the interlayer and the average temperature of the interlayer. This diagram is a vertical air interlayer. The heat conduction between the line 1 and the aperture indicates that the air in the interlayer is in a static state. The heat transfer between the line 2 and the aperture indicates convective heat transfer. The heat transfer between the line 3 and the line 2 indicates the radiation heat transfer when the interlayer is constructed with general building materials. The total heat transfer through the interlayer is expressed between the line 3 and the aperture. It can be seen from the figure that in the total heat transfer, radiation heat transfer accounts for the largest proportion, which is about more than 70% of the total heat transfer. Therefore, it is necessary to try to reduce the radiative heat transfer. Since the radiative heat transfer is related to the surface temperature of the interlayer and its emissivity, the air interlayer can be arranged on the cold side of the envelope to reduce the average temperature of the interlayer, but the effect is not obvious enough. The most effective method is to coat the interlayer wall with a reflective material with low emissivity, such as aluminum foil. In the figure, line 4 and line 2 represent the radiation heat transfer. After one surface are covered with aluminum foil, the radiant heat is greatly reduced compared with without the aluminum foil. Line 5 and line 2 represent the radiation heat transfer. After both surfaces are covered with aluminum foil, compared with the case where aluminum foil is attached to one side, the effect is not significant. Therefore, from the consideration of material saving, it is visible to pass a reflective material on one surface. Think about it. If one surface is fixed with aluminum foil, this side of the interlayer will have a better effect. What protective treatment should be done on the surface of aluminum foil? Next, let's learn the calculation method of the internal temperature of the flat wall, because the internal temperature and the surface temperature of the enclosure structure are the important basis for measuring and analyzing the thermal performance of the enclosure structure. It is mainly used to judge whether there is condensation inside the enclosure structure, or whether the surface temperature is lower than the indoor dew point temperature. Therefore, it is necessary to calculate the temperature of each layer of the enclosure structure. Taking the three-layer flat wall structure as an example, according to the characteristics of steady heat transfer, the heat transfer through the flat wall is equal to the heat flow through each layer of the flat wall. It can be listed that Q equals Qi, equals Q1, equals Q2, equals Q3, equals Qe. Through sorting, the calculation formulas of the inner and outer surface temperature of the flat wall and the temperature of each layer can be obtained, and then the calculation formula of the temperature of any layer in the multi-layer flat wall can be derived. In the formula, the layer number is numbered along the direction of heat flow. It can be seen from the calculation formula of the temperature of each layer of the flat wall that the temperature distribution of each material layer is a straight line and a continuous broken line in the multi-layer flat wall when the thermal conductivity of each layer is a constant value. The temperature drop inside the material layer is proportional to the thermal resistance of each layer. The smaller the thermal conductivity of the material, the greater the thermal resistance, the greater the temperature drop, and the greater the slope of the temperature distribution line in the layer. Next, let's do an exercise. Find the heat flux and the internal temperature distribution through brick walls and reinforced concrete roofs. It is known that the indoor temperature is 15 degrees Celsius. The outdoor temperature is minus 10 degrees Celsius. The thermal conductivity is 0.81 for brick masonry, 0.81 for lime brass, 1.74 for reinforced concrete, 0.93 for cement model, 0.17 for waterproof layer, and the heat transfer thermal resistance of internal and external surface is 0.11 and 0.04 respectively. From the left finger, it can be seen that the roof is a three-layer structure, and the following is indoor and the upper is outdoor. Since the indoor temperature is higher than that of outdoor, the heat flow direction is from indoor to outdoor. The layer number is marked on the right side. From bottom to top, it is 1, 2, and 3. Layer 1 is reinforced concrete 30 mm thick. Layer 2 is cement model 20 mm thick. And layer 3 is waterproof layer 10 mm thick. The right finger shows that the brick wall is a two-layer structure, inside on the left, outside on the right. The layer number is marked on the top. From left to right, it is layer 4 and layer 5. Layer 4 is 20 mm thick lime brass, and layer 5 is 240 mm thick brick masonry. The idea of solving the problem is to calculate the heat transfer resistance of brick wall and roof according to the formula of thermal resistance, then calculate the heat flux according to the formula of heat flux, and finally obtain the internal temperature distribution according to the formula of surface temperature and the internal temperature of flat wall. The heat transfer resistance of the brick wall is equal to 0.471. The heat transfer resistance of the roof is equal to 0.248. Comparing the two, it can be seen that the thermal resistance of the roof is smaller than that of the brick wall. The heat flux of the brick wall is equal to 53.08. The heat flux of the roof is equal to 100.8. Comparing the two, it can be seen that the heat flux of the roof is greater than that of the brick wall, which is due to the fact that the thermal resistance of the roof is smaller than that of the brick wall. The inner surface temperature of the brick wall is equal to 9.2 degrees Celsius. The temperature between layer 4 and 5 is equal to 7.8 degrees Celsius. The outer surface temperature is equal to minus 7.9 degrees Celsius. The inner surface temperature of the roof is equal to 3.9 degrees Celsius. The temperature between layer 1 and 2 is equal to 2.2 degrees Celsius. The temperature between layer 2 and 3 is equal to 0 degrees Celsius. The outer surface temperature is equal to minus 6 degrees Celsius. It can be seen from the calculation results that the inner temperature and the inner surface temperature of the roof are larger than that of the brick wall, also because the thermal resistance of the roof is smaller. Based on this conclusion, you can choose the appropriate envelope structure material for building design and compare the heat loss by using different materials or different structural forms to see which material has better thermal comfort for the envelope structure form. Think about it. Under the same indoor and outdoor air temperature conditions in spring and autumn, the inner surface temperature of the same component obtained by this method is the same, but why is the thermal comfort different?